Thanks everybody for joining today. I'm Andy Pernsteiner, Field CTO at Vast Data. And today I'd like to talk with you about a use case which our customers are using more and more, which is to serve as a platform for their big data applications. And as I go, if you have questions, feel free to put them into the chat. We'll cover them at the end. So let's get started. So if we look back over the history of how big data platforms and analytics have evolved, we can start, we'll say, towards the beginning where Hadoop first made its entrance into the world. And we're talking about over a decade ago, where open source projects, which came out of a few hyperscale companies, effectively were built to be able to handle all of the influx of raw log data and telemetry data that was coming in off of web servers and other large scale systems. And the initial intention behind Hadoop was effectively to allow for the search and index of large amounts of web log data in order to find insights, in order to build indexes and work in a more of a batch oriented framework. And it was very good at what it did. It brought in a couple different components, one of which was the MapReduce paradigm of doing compute on disparate amounts of storage. And then the other was a file system known as HDFS, which was originally aligned to become sort of a distributed data store for analytics data. And it did well at those things, where it was able to allow people to process large amounts of data and store it on commodity hardware using a scale out file system. But it wasn't necessarily the best solution, especially for enterprises that wanted something that was easy to manage, and they wanted something that anybody could learn how to use. Unfortunately, oftentimes, in order to get the most value out of a Hadoop cluster, one would have to understand the MapReduce paradigm for programming. They'd have to have a lot of Java programmers on staff, and somebody would have to maintain this entire infrastructure. And it wasn't really designed for real-time analytics, at least not at first. And so if we take a look at how Hadoop is constructed, and this is still true to this day, even though there are some newer innovations, the basic model is the same, which is effectively that you have a number of commodity servers that have some amount of locally attached disk. Now, if you think about why HDFS was formed in this way, it was to make sure that you could use low-cost commodity storage and hardware to be able to store large amounts of data. And B, there was a goal to put the data and the compute as close together as possible. And the main reason for this was because the networks weren't fast enough to carry the data between nodes in the event where data was remote. So when jobs would run, the processing functions within the node itself, so Spark, Impala, Hive, MapReduce, they would run typically against the data that was in their local attached storage. And that all worked relatively well. Keep in mind that back then, typical servers could do about 2 to 3 gigabytes a second worth of IO performance, but typical networks could do far less. It was not uncommon to have gigabit networking, which meant that the movement of data across the wire was very slow and expensive. So this worked relatively well, but the challenge is that in order to maintain protection of data across this infrastructure, the lowest common denominator method that was used was to triplicate all of the data. So basically taking 2/3 of your storage and effectively throwing it away for overhead in order to survive failure. And the challenge, of course, is that not only are you wasting this capacity, but you're also wasting a fair amount of east-west network traffic to move data between them. Because even though you're computing locally, when data is written, it has to be written to more than one node simultaneously. And so we found that over time, as these systems scale out, they can tend to be less performant and less reliable as they go, because there's a lot of crosstalk and a lot of reliance on this shared nothing architecture. Now, a couple of the big other challenges that we find is that it wasn't also designed for small files or for a mixture of small and large files. HDFS has typically relied on something called the name node, which is a function of the platform that has limits to its scale. So the more files you have, the more pressure is put on the name node. it leads to an unstable system or an unreliable system. And in addition to that, in order to get data in and out of an HDFS system, into and out of a Hadoop cluster, one must have a client that knows how to speak the Hadoop API of some kind. And that means that it excludes other applications from participating unless they're rewritten or unless there's some kind of gateway or layer inserted on top. Now, if you look at the way that Hadoop is effectively constructed, there's a lot of different layers. There's many more components than this. This is just a very small subset of them. But the intention is to help you understand that it's not just one piece. HDFS isn't just one part of it. It's the basis of it all, but in a lot of ways, it's the least valuable thing in this stack. And if you look at what where the sort of use cases as well as all of the innovation are going, they're typically happening further upstream from the file system now. There's much less innovation occurring down at the lower layers. And that's as it should be, because these are the areas where people are actually interacting with data. And what we found is that the elements that popularized Hadoop originally are not necessarily the ones that are the most popular now. So the Hive and MapReduce paradigm, while they're still used by many organizations, they aren't necessarily where the new use cases are going, and people are actively moving to new things that are able to do more with less and do better in terms of real-time analytics, in terms of ad hoc analytics. And so the other thing we've noticed is that the things that are carrying forward, if you think about Kafka, if you think about Spark, if you think about the newer SQL engines like Trino and Presto, they don't really need HDFS. And so what you're left with is a stack that was designed around an original idea to keep the storage and compute close together and to keep it on commodity hardware. But over time, as needs evolved, the platform didn't really evolve with it. And the ecosystem components that are the most valuable parts of that platform, they don't even require that platform. And so customers are looking at different ways of approaching this, which kind of brings us to the next wave of innovation and evolution in terms of how big data platforms are deployed, which is the abstraction wave, where effectively you see a large number of tool chains and tool sets coming to market, which are able to query data where it happens to be. The idea of federation across multiple data platforms and still using the same query tools is becoming very popular. And the idea here, of course, is that you don't have to make extra copies of data. You don't have to move it from place to place, and that your engineers or developers can work directly on data sets without having to go and engage in complex ETL pipelines to be able to get it to the place that they need it in. But it isn't necessarily the end stop. It was designed to start to allow people to migrate these workloads into the cloud. And so you'll find that most of the applications today are able to support S3 as the primary API that they communicate with storage. And while that's the case, it doesn't necessarily solve all of the problems. It still results in more platforms, more silos. In fact, if we look at a very common use case would be to have silos for every different type of use case or workload that you're running. So you might have one that's more focused on batch processing that could live in Hadoop and HDFS today. You may have the need for data warehouses that are talking directly to their own storage or offloading to a separate store in order to maintain performance and to hit the right cost curve. And data scientists are oftentimes using tools that aren't compatible with a Hadoop file system or that aren't compatible even with S3 object storage. It's very common for people to be using frameworks which were written in a time where POSIX file systems were more common. And because of that, people are making copies of data. They're moving it around and they're managing multiple copies in many different scenarios. And part of the challenge with making copies isn't just that you have extra copies of data. It's that you need to make sure that people know which copy of data they need to be interacting with. And in cases where you care about the results being extremely accurate or up to date, you also have to find a way of making sure that all of these things are kept in sync in some way. There's lots of technologies, products out there which are helping people to keep these things in sync, but it's a problem that they're solving that doesn't need to exist. If you have a way to consolidate everything, it's not necessary that you come up with all of these strategies to be able to move data around and transform it. So what we've decided is that there's a new way of approaching, which is similar to wave 2 of abstraction, but what we call disaggregation, where not only are we moving the compute and the storage further apart from each other, but we're also allowing for consolidation of other workloads, even when they aren't necessarily traditionally the big data style analytics platform workloads. And so if we start to look at how we're able to do this, the reason why is because the networks have come a long way in the last several years, especially in the last decade. We're seeing customers deploying 100 gigabit and even 200 and 400 gigabit Ethernet and InfiniBand products into their environment, which means that the bottleneck is no longer on the network layer. And because of that, there's no need to keep data local with the storage. I'm sorry, no need to keep the compute and data storage tightly coupled together. And it means that you can start to do many other things in terms of flexibility to be able to allow clients who are running different data centers, who are running in different environments, to be able to access all the same data. And in addition to that, not only has it gotten much faster, the latency has gotten much lower, which enables people to do things they weren't able to do before on traditional scale out HDFS style platforms. Hadoop is never really known as a low latency platform. It was always typically thought of as a batch oriented system. And so what we found is that customers may have built their pipelines around Hadoop, but then they always have some other lower latency applications that are running somewhere else. And that's because the low latency applications couldn't run on that platform. And taking advantage of the advances in networking and compute today, we also see a new advent, which is the ability to do RDMA between endpoints. And it's becoming much more common for applications and servers and networks to support RDMA as a transport, which can remove a lot of CPU overhead and burden from the compute engines that are running these analytics applications. And the advantage, of course, if you're able to use RDMA, is that you don't have to waste CPU time on doing I/O. And the next evolution from that is the ability to start taking full advantage of GPUs in the same vein. So what we're starting to see is there are vendors as well as open source initiatives to use GPUs directly for analytics. There's several private vendors in the space. Also, NVIDIA has put in a fair amount of time and effort into improving the version 3 of Spark to include support for GPU. And because of that, we're starting to see more GPU applications trying to gobble up all of this analytical data. And if you can couple RDMA and GPUs together, well, you've then created a system where you can get the best in class performance for analytics operations without wasting any CPU time on moving data over the network. And so these are things that we see as being possible in the analytics space, but you need a platform able to support it. And so because we're seeing all of these things happen, if you remove the limit on the networking side because the networks are faster, and if you started to remove the limit on the computing side because GPUs are able to crunch these numbers much more efficiently, then you need something underneath it which can feed the GPUs, which can feed these next generation applications. And that means you need storage that can keep up not only with the network, but also with the compute. And the other thing that we're finding is that now data sets that in the past people might have thought of as being large if they're over maybe a petabyte or two are now a fraction compared to what they are today. Meaning we see people now who are deploying 50 or 100 petabyte systems or above just to be able to perform analytics. Whereas maybe 5 to 6 years ago, they were in the low number of petabytes and growing at a relatively slow pace. As the data sets get bigger, as the networks get faster, as the compute gets faster, the storage must get faster. And so the latency really impacts how well analytics can be done. Because if you consider the general machine learning and AI flow, it all starts with iteration. It all starts with being able to identify patterns in data and continue to iterate over and over again. And the longer an iteration takes, the less likely it is that you get the insight that you're looking for. And what we've also found is that many times organizations will tier from some higher cost, higher performance tier of storage down to something else, down to some hard drive based or even slower type of storage in order to save in cost. But the challenge with that is that the savings that you get from that isn't necessarily going to allow you to get the most out of your investment, because you're effectively wasting a lot of very precious compute cycles moving data around and ensuring that data is in the right place. And ultimately that ends up becoming more of a bottleneck in terms of cost than the storage itself. So let's talk about what the architecture could look like if you were to use something new. And of course, I work for Vast Data, and we are out there working with customers to deploy large-scale all-flash architectures for a number of applications and use cases. We tend to see big data and analytics applications as a new driving force in people who are adopting all-flash architectures. And we're right there at the beginning of it, in part because of our disaggregated nature, and in part because we're offering a very cost-effective way to migrate data to all-flash namespaces. And so to give you some examples, right? So we built a platform that is 100% flash-based. We have no spinning disk within our architecture whatsoever. We have multiple types of flash, and rather than get into all the architectural details, I'll kind of give you the high-level benefits. One of which is that we can allow our system to scale in terms of compute and performance and capacity independently of each other. So we have a multi-layered architecture where at the bottom layer, you have some number of storage enclosures which contain all of the state of the system. And at the upper layer where it says stateless servers, that's where all of the work is done from a storage and IO standpoint. So clients who are speaking the S3 API or NFS API or SMB protocol, they would all speak to one of those stateless servers, and those stateless servers are responsible for doing all of the work. This means that the servers that are doing all of the work don't have any state, and it means that the hosts that have all the state don't need to do any work. And this gives us some advantages, because it means if one of the working servers fails, it doesn't matter to us, because we don't have to rebuild data. We don't have to redistribute it. Because of the way that we are leveraging this NVMe over Fabrics connectivity from the stateless servers down to the storage enclosures, it means that all of the stateless servers can see all of the devices that are in the storage enclosures, which is a complete different approach to doing scale out systems, because it means that there's no ownership of data from one server to the next. That ownership and lack of ownership in our case really makes it so that we can scale, and so that we can do things like scale out the compute or stateless layer at a different rate that we scale out the storage layer. If you need more performance, add more compute. If you need more storage, add more storage enclosures. You don't need to add both. You don't need to waste network ports. You don't need to waste time, money dealing with any migrations of that sort of nature. And of course, we built this initially as a file system and object store, which means that we support multi-protocol to all of the types of data that are landed on our system. So if data is written over, let's say, S3, it can be read or modified using a POSIX standard file system call over NFS or SMB. And we've seen customers who are developing pipelines which write data using one protocol and read them using another protocol, and they don't have to make a choice on which applications that can interact with the system. We've spent a lot of effort, because of our focus on extreme networking, to make sure that the performance is always at the forefront of how we deploy our systems. And we've made sure that everything that we ship can be used in an RDMA capable environment, both with GPUs and without. Now, typically, customers will deploy a variety of applications when they access our system. It's not just that they would use analytics. It's not just that they would use AI or machine learning. It's not just that they would use us for a log store or something along those lines. They'd use us for all of these things, because we're able to carve up the system in a way that allows all of these workloads to coexist together. But obviously, building out an architecture that's all flash and uses next generation technology, it sounds like it's expensive, right? It sounds like it would cost more than what you might be accustomed to using today. And we've tried to approach that from a number of different layers. The first of which is that we only use commodity grade. When I say commodity, I mean consumer grade flash. And today, that's in the form of QLC flash. And QLC, for those of you that don't know, means that there's 4 bits per cell, which is the next iteration up from TLC, which is 3 bits per cell. As the flash gets denser, it also becomes less endurance, which means that the the next step up, let's say PLC, which will be 5 bits per cell, will be less endurant than the previous generation. And so a lot of our intellectual property and a lot of our file system developers' time was spent ensuring that we would treat the flash as gently as possible so that we could always use the lowest cost commodity flash, not just today, but also in the future. And this is a huge advantage when compared to other all flash implementations because they will typically use high endurance enterprise grade flash. And that comes at a premium, right? So we typically find that even just based on the cost of the hardware, the systems that we provide to customers are significantly less expensive than another system. So that's the first simple thing. The second thing is that instead of doing things like triplication of data or even a short RAID stripe for data, we do extremely wide stripes. And part of the reason we're able to do this is because of that architecture I mentioned earlier, where we've disaggregated the compute and the storage, and we use multiple types of flash in order to be able to make sure that our stripes can be very wide. But it saves a significant amount of overhead in terms of what people would consider data protection overhead. And so the system starts out at around 10% data protection overhead, and as it scales, it actually goes down to around 2 to 3% for data protection overhead, which is significantly lower than any other system that you can source. And then the last thing, which is really a lot of magic in a lot of ways, is that our engineering team has built an always-on data reduction platform, which effectively means that every time data is written to the system, it can be deduplicated and compressed against any other piece of data that was already written. So it's very unique, and it allows us to get much more efficiency out of the storage overall, which of course ultimately saves people money when they're trying to migrate to it. Now, if we think about how this would look, and it's very similar to the previous slide, but I wanted to kind of give a little highlight in terms of how people are using it today. We don't think that we're just going to serve one workload or another workload. We're trying to serve them all and do so in a way that allow for people to have an ecosystem that they can layer on top. Now, just to be clear, we're not building the compute layer for customers, right? We don't run the compute nodes. We're not running Spark clusters. We're not running Trino or Presto clusters. That still is the responsibility of customers to be able to build and maintain that. We're acting as a very highly resilient, scalable, performance storage subsystem that's a very beneficial alternative to migrating into HDFS or into another platform. And for all the reasons I mentioned earlier, because we're able to scale our system out for performance as well as capacity, we're able to expose it using a number of industry standard APIs and file system protocols so that all types of applications can work. We can be the backup repository over NFS for, let's say, a data warehouse application. We can be external table storage for data warehouse applications. We can be the storage of record for incoming new transactions that go through a database such as Postgres. We can be the storage that is queried by Spark or Trino or Presto, where people are also running machine learning and AI experiments on the same data, because we're not making restrictions on how that data is accessed. There's no sort of wall in our system that says that data needs to be accessed one way or another way. And it was designed to be extremely scalable. We have systems today, and we've only been in business for around 4 years. We have systems today that customers are using in production that are over 100 petabytes worth of usable storage in a single namespace. And that's just the beginning. We've already had them tell us that they're going to continue expanding those systems and migrating them over time. And we definitely designed the system to be exabyte scalable, not only in terms of capacity, but also in terms of performance and the amount of machines and users that can access it all. Another thing that I probably didn't touch on is that it doesn't matter which type of protocol or API you use to access data on the system, it's all going to be effectively the same speed. So the system that we deploy will allow you to get best-in-class performance for not only NFS applications, but also S3 on the same data sets, and they can all enjoy that sort of fast access to data. And because it's all flash, there's effectively no seek time. So the latency is extremely low and predictable as you scale workloads out. Okay, let's just get into a little bit of a comparison to make sure you understand some distinctions. And I'm not going to go into all the details, that would take too long, but effectively, uh, there are other options that you have, right? There are other commercial options that you can use, which are serving a very similar purpose in the sense that there are enterprise storage vendors who have systems that can speak NFS and can speak S3. So why would you choose VAST over one of those? Well, the first of which is that we've built our system on an architecture that was designed to be infinitely scalable because we have disaggregated the compute from the storage, which if you think about it is very similar to disaggregating the compute and storage in the analytics space itself, right? Moving from a sort of locally attached HDFS implementation to moving to where your compute and your S3 objects stored in two separate physical systems. That's a disaggregation on its own. We actually take that disaggregation to another level by creating a storage system that's disaggregated. And so obviously we're very linear in terms of scaling. We're also much more scalable. So if we compare ourselves against, in this case, Pure FlashBlade, which is another all flash scale out object and file system, we have significantly better scale, right? And so our systems that we have on the floor today can reach over 100 petabytes. They're limited to around 5 to 10 petabytes max size. And so it makes a pretty big difference. We also, because we've created this shared everything architecture, we're not plagued by the same issues. And so if you look at some sort of piece by piece, comparison points, the challenge that you have is, of course, they have very good marketing that explains how their system works. But if you dig back and look through the layers, they haven't actually done anything that new. And so because of that, the system can't scale nearly as large as our system can scale. And from a performance standpoint, you're never going to get anywhere near the same levels. It's very common for us to go into environments that are using this existing FlashBlade platform and replace it because we can double or even triple the performance for a lower price point, and we allow for the system to scale to a much larger point because oftentimes customers don't know how large they need something to scale, and so they need something that will be there even if they get to double or triple or even larger amounts of data sets in the future. But obviously, comparing us to an enterprise vendor isn't necessarily a fair comparison, given that a lot of people who are migrating from HDFS are looking at open source alternatives. And so MinIO is one open source alternative, whether you pay for it or not. It's using open source software under the covers, so it's open in that sense. However, if you really think about how it's built, you have to make sure that it's accomplishing the goals of your architectural needs. So the first thing is that everything they've built is still built on a shared nothing architecture. So every server owns some data, and they do sharding and distribution across those servers. It's very common practice. Problem is that can lead to crosstalk between the servers and ultimately can impact the scale and the resiliency and performance of a system. Another obvious glaring point here is that they're only supporting S3 as a transport method to get data on and off of the system, which means that you're limited in the applications that you can deploy. You can't just deploy anything, especially if the application you have is a more traditional database or application that requires that people can make modifications to existing files. That's not something you can use on S3, which does limit how you can fit it into your platform. Now, ultimately, MinIO is sitting on top of an existing file system. They don't build their own file system. They have a layer stitched on top of one, which means that there is some limit in terms of the performance they can extract. Whenever you have a layer in between the hardware and the ultimate software, if there's more than one layer, then you effectively put yourself in a position where you're wasting IO, and you're also losing some of the benefits that you would get in terms of data reduction, because, for example, the only compression available on MinIO today is what's called local compression, where each object gets its own compression, which can be useful for very sort of compressible data sets, but isn't so useful when you have a large corpus of data and you're compressing everything independently. One example that I would give is that local compression is as if you were compressing a single file one at a time. You'll get some benefit out of each single file, but if you try to compress those two compressed files against each other, you don't get anything extra. Whereas the way that we've implemented data reduction is global in nature. So every new block that comes in gets compared against every other block on the system. And if it dedupes, then we don't have to store anything. If it is similar to other blocks, then we can compress those similar blocks against each other, and you get the benefit of compression when even the data was written in a previous case, right? So we've definitely got the edge there. And then ultimately, we designed our system to be an enterprise platform that customers can scale, they can manage, they can maintain, they can monitor, they can grow. And we've done so in a unique way, but ultimately, we're an enterprise storage class system. And so what that means is that customers have some demands that they place on us. They need to have proper monitoring and reporting. They need to have a UI that's easy to use and is able to be flexible. They need an API that is flexible, effective, documented, and supported by a series of engineers and support engineers. And the challenge, of course, is that MinIO started with something that was meant to be for an individual user to run an object store on their laptop, and then maybe scale it to something a little bit larger than that. It wasn't really meant from the beginning to be a massively scale out system. And it shows. The customers who have MinIO deployments typically keep them small because they're challenging to manage at scale, and they have some issues at scale. And speaking of scale, generally, they have different concepts that people have to learn, and ultimately there are challenges in terms of upgrading, in terms of expanding, in terms of contracting, in terms of dealing with maintenance operational issues. There's a lot of extra waste that ends up happening because there's a lot of buffering and extra storage required to be able to protect data and to make sure that there is enough room for data to be coming in while all these protection and sort of rebalancing operations are going on. But why move off of HDFS? Why move off of Hadoop in the first place? I think we're starting to see that there are some movements within the industry, especially if you look at Cloudera's sort of history. If you go back in time, there were, let's say 3 major Hadoop vendors. One of them kind of shut down, the other one got gobbled up by Cloudera, and now Cloudera themselves has been taken over by private equity. And from the outside, we can't tell everything that's going on there. Obviously, there are sort of financial challenges they may be having. But the simplest, obvious way that we know that there's some movement away from it is that they're changing their licensing model. And typically, companies don't do that unless something's going wrong. And so what we're finding is that customers are being placed into a situation where they're being told they have to migrate to something new, and that the license bill that they currently are paying is going to go up. And so we're seeing more and more people start to look at other options. And one option is that you could migrate into Cloudera's new platform, which includes a backend storage subsystem known as Ozone. Ozone is effectively an iterative attempt to make HDFS more palatable, right? So it can speak to Hadoop applications using the standard Hadoop APIs. It now exposes the system using the S3 API as well, which is an improvement. It does allow them to do a little bit more. But the truth of the matter is that all of these Hadoop applications can speak S3 anyway. So there isn't a huge advantage in terms of now exposing this data over S3. And it's still based in the same underlying architecture. Now, they may have made some improvements in terms of how metadata is stored and in terms of the scale of the number of objects or files in the system. But ultimately, it's still the same thing. It's based on the same underlying technology. And it still only exposes itself using some very basic and sort of object-centric APIs. There's no support for a modifiable file system. There's no support for NFS that's native. Anything would have to be done through some kind of a gateway, which of course impacts performance. And it's still in the same boat of having to replicate data 3 times by default, which ultimately means that you're paying 3 times the amount that you need to, which means that if you're thinking about building a platform that's based on Flash, you have to think twice, because no one wants to pay triple for the Flash that they're buying. They want to be able to pay the least amount possible. And so, unless you're looking at an archive application, we don't think that Ozone is a great path forward. And so if we look at sort of a side-by-side comparison of how we would compare and contrast ourselves when deploying a system into a Hadoop environment. We typically find that most customers are deploying Hadoop in a way that is more capacity optimized than it is performance optimized. And what I mean by that is that when people are deploying HDFS, they basically scale the number of Hadoop nodes based on the amount of capacity or storage that they're storing. And they have a relatively fixed size of server they continue to add, right? Let's say your servers have 10 terabyte drives, there's 12 of them. So it's about 100 or so terabytes per server, of which you're only getting about 30. And so if you want to build a system that is 10 petabytes of available capacity, you need a lot of servers in order to do that with HDFS. And the performance that you get out of that based on using sort of lower cost hard drives is going to be significantly lower than you could get off an all flash system. Now, this really kind of shows itself when you consider that to build a 10 petabytes file system using HDFS, using some standard commodity servers, you'd need about 30 petabytes of raw capacity. And once you're in that realm, you're also considering how many racks and how many servers you need, what the power and cooling is, all the things that you don't want to have to think about, but at some point somebody needs to. And it can be significantly more costly to deploy a system of this size. Whereas deploying VAST, you can get all of the 10 petabytes into a single rack worth of hardware, and then you can decide what the compute layer needs to be. If you're running Spark, if you're running Presto, you don't necessarily need to scale all of your compute to match the amount of storage that you have. It really depends on the workload. And giving people the flexibility to scale those two things independently means that there's significant opportunity for cost savings. This is not just hardware savings, this also can be license cost savings. And this was the primary reason where one of our kind of marquee customers is migrating all of their Hadoop environment over to VAST. They are actually running self-supported Cloudera HDFS and Impala. They're not paying support for it. But even though they're not paying anybody for HDFS, they still thought that it wasn't the solution they wanted to carry forward with. They'd much prefer to leverage an enterprise system that was very cost competitive. And they did their due diligence. They ran a POC with us where they tested both MinIO on all flash NVMe storage and VAST. And in the case of MinIO, the cost was significantly higher and the performance wasn't higher. And in fact, because MinIO and other object stores don't support other protocols like NFS, they weren't able to extract the most value as they needed to, because it turns out that some applications, even in the Hadoop stack, perform better with POSIX file systems than they do with S3. Impala is one example of the application where the ability for it to do ranged random reads inside, let's say, Parquet or ORC files was significantly impacted when it moved over to S3 because it would try to fetch the whole object, which obviously is a waste of IO, a waste of compute and memory. Whereas over NFS, it would only fetch the relevant pieces of those columnar files that it needed, and it would result in lower overall query runtimes. And so for them, they have over 100 petabytes in HDFS, and they're migrating petabytes every single month over to VAST because they're able to do so without disrupting our applications and giving their applications a better platform to run on, more performant, more scalable, more reliable. And so if we really think about the overall macro picture here, we've built a system that not only for big data, but in many ways, especially for big data, can allow people to scale out a data platform to an extremely large size in both terms of capacity and performance. It allows them to consolidate all of their workloads into a single platform, not just the sort of data science experiments, not just batch analytics, not just real-time analytics, but all of those things, and do so in a way that is cost effective and allows for future growth, both in terms of capacity, but also in terms of the types of applications that are used. And so, I think that the high level that we take away from all of this is that people are starting to migrate away from traditional architectures and move to something new and modern. And we have taken the best bits of the new and modern world and taken the best bits of the previous world and combined them in a way that let people not only carry forward the applications that they're used to using, but then also start to explore the utilization of new ones in the future. And that's all I got. So me check and see what questions we have. So there was a question from somebody around Hyper-V or VMware block support. We do have support for being able to integrate with VMware. We're working on Hyper-V support. We find that to be less of a concern in most big data and analytics shops, only because they're typically not running block-based applications. But we do have some answers and some options for people in the block space. So another question that we commonly get is how people would migrate data from HDFS into VAST. And of course, there's tools that can do this, right? There's DisCP, which is a Hadoop tool that can be run in parallel to copy lots of data over. And we see that being run for some sort of batch data. In terms of migrating other applications over to VAST, typically we find that people don't do these things all at once, right? It's always going to be sort of piece by piece, because you have to migrate, you have to test, you have to cut over, then you sort of move on to the next thing. And generally, because Hadoop, the compute layer, has a pluggable storage model, it basically allows for people to sort of switch in different types of technologies or storage technologies without having to migrate everything all at once. Another question that I just got would be, can we be integrated into an existing Cloudera farm, or would it require a net new next generation cluster? So we would deploy a VAST cluster, which would run on hardware that was exclusively for that use. However, an existing Cloudera deployment that was running, let's say, 100 compute nodes with HDFS attached, could point to the VAST cluster as its data repository for some or all of the data sets. Now, obviously, if you already have 100 servers with direct attached storage, you don't want to throw the storage in the garbage. You're going to continue to use it. But as new workloads come in, if they are better run in a higher performance system, you would start to bifurcate where that data goes and start trickling it onto the VAST system. Over time, obviously, you would want to retire those older Cloudera server nodes, only because they would have a high probability of failure, which you wouldn't want. There is another random question someone sent that's not really relevant to this big data conversation, but it's around our thoughts on Intel's Optane devices and what that impact is for us. And the truth of the matter is, we've been anticipating this for over a year now. Intel hinted to us quite some time ago that they were not sure about the direction that Optane was taking. And so we took steps over a year ago to make sure that we were dual sourced and even tri-sourced in our supply chain. So not only do we have supply for the next several years of Intel's Optane product, but we also have another vendor that we've been shipping product with for over a year. And we are looking at yet a third vendor in order to supply that as well. And so there's no impact to us. We have actually no challenges in the supply chain space right now. Typically, customers who want to deploy systems don't have to wait more than 3 or 4 weeks to get them on site. So we don't have an issue on that side of things. Let's see if there's any more questions, and then we can wrap it up. Another thing that people ask about is S3 compatibility. And while we aren't 100% compatible with all S3 verbs that exist, we've done extensive testing with several applications, specifically with Trino, Presto, Spark, Dremio, Hive, MapReduce. I could go through a long list, and have made sure that we are compatible for the operations that those applications need to use. We also have other customers using us for other S3 use cases, and of course have focused on the S3 APIs, which are most critical for those. And we've added lots of things, including support for S3 policies for doing security management to make a more unified way of securing access. We can replicate data from one data center to another, so that you can have S3 applications access data in more than one data center. So there's a lot of different things that we've added on the S3 side of things, but that is something that sometimes people ask about. And the last of which is, I mentioned security. I've always taken the approach that security is best done at the layer where the data is held, because anything on top of that is an abstraction, and it could potentially provide for alternate means of access. So we handle all security at the file system and object storage layer, using a combination of ACLs as well as policies, which can be very granular and provide rules to access data, so that administrators only have one place to go and look to determine how their data is secured. So I appreciate everybody taking the time to jump on today, and I hope you have a great rest of your day.